We're going to keep doing optimization. We're not actually doing anything new, just doing more examples here. And hopefully this is good practice for y'all. So in this case, we have Farmer Bob, and he needs a big container to store all the milk from his cows. And he wants a cylindrical can that is going to hold 1,500 cubic centimeters of milk. So one thing that we noticed that, especially based on the fact that the units here are cubic centimeters, that this is a volume. So the volume is going to be 1,500. That's going to be our constraint. And then we want the dimensions that will minimize the amount of material used. So that means that we want to minimize the surface area. Okay. And so you might need a little bit of help remembering the surface area and the volume of a cylinder. And on a test or quiz, I would give you these formulas if you needed them. So, but it is always good to be able to recreate them also. So for a cylinder, we have a radius and a height. The volume of a cylinder is pi r squared h. What you want to think about there is that the volume of, or that the area of the base, it's a circle, its area is pi r squared, and then you multiply that by the height. So kind of like adding up a bunch of circles there. Okay, so that is our constraint for this problem, because we know what that's equal to. And then the thing that we're trying to minimize is surface area. I'll call this A. So the surface area of a cylinder comes from the surface area of the top and the bottom. So those are our circles. So those are the, what's this called? The area of a circle is pi r squared. And there's two of them. So we're going to have 2 pi r squared. And so that gives us the top and the bottom. Then we have to figure out the surface area of the sides. And let me tell you how you would recreate this. So you would think about the cylinder. Let me make a cylinder here. So think about the cylinder, think about cutting it straight down and unraveling it. So if you unravel a cylinder, you get a square or a rectangle. And so this side of the rectangle is the height. And then we need this length. And so if we multiply this length by this length, we're going to get this area. So this length, if we re-roll our cylinder, that length is coming from up here. That's just the circumference of the circle. So in order to find the rest of the surface area, we have 2 pi r, because that's the circumference of a circle, times a height. Okay, I just like to be able to recreate that. Again, I'll give you this formula in a test, but it's so nice to be able to recreate it. Okay, so that's the thing we're trying to minimize. So, as always, we're going to need to solve the constraint for one of the variables. I'm going to solve for h because r is being squared and will just be messier. So if I solve for h, I get 1,500 over pi r squared. And then I'm going to plug that in. This one is just kind of a messy looking problem, but is not going to be too terrible. 2 pi r times 1,500 over pi r squared. Okay, now remember, we're going to try and find where this surface area is minimized, so we're going to need to take a derivative. Let's simplify things before we do that. So one of these radiuses is going to cancel out, and the pi is going to cancel out. So my surface area formula will be 2 pi r squared plus 2 times 1,500 will give me 3,000 over r, which is r to the negative 1. Okay, so now we're going to take the derivative. So we get 4 pi r, not r squared, r to the first power plus, nope, minus, because we're going to bring the minus 1 down, minus 3,000 r to the minus 2. Okay, we need to set this all equal to 0 and solve for r. I'm going to rewrite the r to the minus 2 as r squared in the denominator. Okay, so now if I keep solving this, let's add the 3,000 over. Let's multiply both sides by r squared. So we have 4 pi r cubed is 3,000. Okay, all the r's are together now, so this is good. We can divide by 4 pi. And now we can take the cube root of both sides. So this problem is not really like a hard problem. It just has some messy algebra in it. Okay, so when we solve this, we get 6.2 out. If you type that into a calculator, it's going to be a little bit easier to think about it as 6.2. The units here will be centimeters. Okay, so this is probably our radius, but remember that we need to check and make sure that this is actually a minimum. Okay, and so we should ask ourselves, do we have bounds here? Do we have a closed interval that we're working on? And so the thing that we know is that the radius the smallest that it can be is 0, but it can never actually be equal to 0. And the biggest it can be is anything because we could just have a really long, skinny cylinder that could keep going on forever. So we don't have any bounds here. So we're going to need to do a number line, use the first derivative test here. So on my number line, I'm going to put my 6.2. I have my A prime. And so let's see, we're going to plug numbers into the derivative. So this was my derivative. So let's plug in a number a little bit bigger than 6.2, like 7. If I plug that into the derivative, double check and make sure, but you should get a positive number. And if I plug in a number smaller than 6.2, I'm going to get a negative number. Remember that we can't plug 0 into this, so be careful, like plug in 1 or something like that, or 6 would be sufficient as well. So the fact that we get a positive and negative and we only have one critical number tells us that this has to be our absolute min. So our absolute min occurs at r equals 6.2. And let's see, the problem asked me the dimension, so I also need to report what the height is going to be. We have a formula that relates the height and the radius, so the height will be 1500 over pi times 6.2 squared. And let's see, that ends up giving us 12.42 centimeters for the height. So 12.42 for the height and 6.2 centimeters for the radius are the dimensions here.